Welcome to the 13th video in Introduction to Quantum Field Theory. This is the second video on Noether's theorem, specifically on internal symmetries, and this will be the last video in the first part of this introductory series. The next part will cover free fields and go more in depth into quantum mechanics and blah, blah, blah. This was just the introduction to the introduction. So, just a little bit of recap. Noether's theorem is that for any continuous symmetry within a physical system, there exists a corresponding conserved quantity. Now, with internal symmetries, there are amounts or numbers or quantities that are internal to the field. So they don't exist outside of the field. Like for example, the position of an object in space, um, something existing in space is external to the field. So it's called an external symmetry or a space-time symmetry. So we will be dealing with internal symmetries. Two examples of that we will consider are field shifts and phase shifts. And we'll see that field shifts lead to the conservation of conjugate momentum, or also more generally like something called Noether current. And we'll see that Noether current um, directly relates to the conservation of charge. So let's consider a field shift. A field shift. C maps to C prime. This is C plus delta phi. So there's some change. And we're going to assume that this change is very small. So for any n, or so for n greater than 1. So if n is greater than 1, then this squares to, or this will have this to the power of n greater than 1 will be approximately 0. So this cannot be directly be seen. So a field shift like this, which can, okay, cannot be directly seen by an experiment, or this is, so this is this needs to be more nuanced than what I'm saying here. What I'm saying isn't exactly correct because it's not nuanced, but we'll just go with it. Which cannot be directly seen by an experiment. So it is indeed a symmetry. So we need to do the same thing we did last time, which is consider the shift, or the change in the Lagrangian density. So this is the Lagrangian density of the new field. So plus this plus this minus the original Lagrangian density. Well, this is, if we recall, the property of a differential. So let me go back up to this property because it's very important. We're taking the differential of something. So if we take the small change in it, then it's going to be f is equal to big F, or plus the function that's being input to it. plus the small amount of change, and then in the direction it's changing, the rate of change in the direction it's changing. So we're going to come back down here and we get the original function. So phi partial mu phi, then plus the amount that it, or plus the rate of change of the Lagrangian, plus the amount it changed by. And then we have two variables that on which it depends. So we have to do this for both variables. So these are the partial mu here distributes to this, and so that ends up being here. This is the change in that direction. Then minus the original Lagrangian density. Okay. Well, these will cancel. So we can get this. And then going here, we can make a substitution. We can substitute in this. This is the Euler-Lagrange equation. This is the Euler-Lagrange equation that we derived a couple videos ago. And we're going to insert it into this. So we end up with, I'm just going to copy this. Copy this, d mu, then you get delta phi plus this amount. Move them apart a little bit so it's easier to distinguish. And now we're going to move to the next one using the product rule. So you have you have partial mu of this times this, and then you have this times partial mu of this. So you can combine them together to get partial mu of the total system. This. And we know that this is equal to 0 because if we're dealing with the symmetry, this must be equal to 0. So then this quantity right here, I'll do this. This quantity is typically written J mu, and it's called Noether current. And so now, if we have a field shift, we see that there is some conserved quantity, and that is J mu. It is Noether current. So we can write this as, or if we have a field symmetry or a field invariance, then Noether current is conserved. So conservation of Noether current. And an interesting thing is, oh, hang on, I don't like that. Interesting thing about this, there is an amount that is defined from this. So if you take the change in the time direction, so you take the Noether current in the time direction, and then you divide out this change in the field. So you can notice that the change in the field is divided out here. This is conjugate momentum density. And there's another quantity, Q, which is the integral over space, not space-time, but over space of the Noether current's time-like component. And this is called Noether charge. So these are all things that follow from a field shift. Now let's consider infinitesimal phase shifts. Let's consider infinitesimal phase shifts. These phase shifts are actually, I want the colon here. We're going to be considering a complex field. So you have the real part, or you have the field, and then you have the complex conjugate of the field. And these will map to C, or you'll have some phase rotation times the field, but this will be an infinitesimal rotation. So 1 minus I epsilon phi is equal to phi minus I epsilon phi. And you have an identical rotation here, and that's just going to be phi dagger plus I epsilon phi dagger. So these are your new mappings, your phase shifts, infinitesimal phase shifts on a complex field. And so that implies that the change in the field is equal to negative I epsilon phi, and the change in the complex conjugate field is equal to I epsilon phi dagger. Therefore, we can consider the Noether current for each field. So we can say that this is the one for just the normal field. Just for phi, get negative I epsilon phi, and there is a corresponding Noether current for the complex conjugate. Which is going to be I epsilon phi dagger. And the total current, because this is a complex field, the total current is the sum of the individual currents of the normal field and the complex conjugate field. And the Noether charge here is the integral over space of these two quantities. So copy this. I'm going to bring out this epsilon. I'm going to bring out an I epsilon here, and plus this right here. So the Noether charge looks like this. And it turns out that actually this Noether charge corresponds to particle density, so the number of particles in a system. And if you then multiply this by charge, then this implies conservation of charge by conservation of particle number. So the conservation of particle number and the conservation of electric charge are actually a result of phase shifts in the field. So this was, of course, for a scalar field, but the same results will hold for a spinor field. So that's where you get the electric charge conservation.